than participants joining. It's probably a heavier tail.
And the patients hopefully won't burn out.
What's that? With me or with the participants? There was, don't worry, people are muted. There was a lot of laughter. I could tell.
Sorry, Prasad, I didn't get it. What did you say?
I took the analogy further. If he waits too long, some kernels burn.
Ah.
Okay, so yeah, let's get started. Yeah, it's a pleasure to have Shravas here, who will tell us about sparse reconstruction for Hadamard matrices, or sampling from Hadamard matrices.
So yeah, so thanks for having me. Thanks for the organizers for putting this on. I was super excited to maybe be in Berkeley now, but I'm glad that we're still doing this workshop through Zoom. Cool. So as James said, I'm going to be talking about this paper, an improved lower bound for sparse reconstruction from subsampled Hadamard matrices. And this is based on joint work with a bunch of people, including Jaroslav Blasiak, Patrick Lopato, Kyle Law, and Jake Marcinek. So before I get started, I just want to mention a few things. First, the paper that this is based on is a little bit short, so definitely don't be shy in asking questions. We definitely have lots of time to answer questions. And then the other thing I'll mention is that I'm going to talk about sort of a few warm-up ideas that aren't in our paper before we actually talk about the ideas in the paper. So probably we won't actually talk about Hadamard matrices until, say, halfway through, but I'll bring that up so that way you know what to expect. Cool, so let's get started. So basically the object we're going to study are the set of k-sparse vectors, and they're going to live in, say, a big n-dimensional vector space. Once we start talking about Hadamard matrices, it might be helpful to index our coordinates by vectors and say f2 to the n. So for now, we'll just stick with, say, a capital n-dimensional vector space. But when we talk about Hadamard matrices, it will be useful to say it will be useful to index the vector, or index the coordinates by f2 to the n. Cool, and there's a few reasons why we might care about k-sparse vectors. One reason is that many real-world vectors are sparse. Cool, and then another reason, and I don't know if this is like a real reason, this is maybe the reason I'm a little bit interested in sort of studying k-sparse vectors, is that these vectors have a bound on, say, the ratio between the L1 norm and the L2 norm. Right, and if we sort of extend our object to say all vectors that have a bound on the ratio between the L1 norm and L2 norm, a lot of the upper bounds still hold, and of course, for lower bounds, if we consider more, if we extend our space of vectors that we're considering, that's not going to hurt anything. Cool. And sort of the question we're going to ask is, how can we embed k-sparse vectors in a smaller dimensional vector space while still preserving the geometry? Right, so these sparse vectors are vectors with a lot of zeros, right? A lot of these coordinates are zeros. And when we're looking at any, say, single k-sparse vector, it feels like maybe we're wasting a lot of space, right? Because there's a lot of zeros. On the other hand, it kind of also feels like, well, we need every single coordinate because we won't necessarily know which coordinates are non-zero, right? It could be any set of, say, k coordinates can be non-zero. Cool, so we can ask this question, well, like by how much can we actually sort of, well, how can we embed these k-sparse vectors in a smaller dimensional vector space? Cool, and sort of the property we're going to be looking at is something called the restricted isometry property. This was introduced by Candace and Tao, and what this says is that if you have a matrix A, this matrix, when you multiply it by an n-dimensional vector, is going to give you a q-dimensional vector. We say it satisfies the restricted isometry property of order k with constant epsilon if for all k sparse vectors. The L2 norm of a times x squared is approximately equal to the L2 norm of x squared. Cool, so basically if we multiply this matrix A by a k-sparse vector, we're going to approximately preserve the L2 norm squared. Cool, so in some sense it's like an isometry, but just this guarantee is only for k-sparse vectors. One thing that I think it's helpful for me, at least when I'm thinking about this, is to maybe think it's like the opposite of normalize, but say look at sort of the L2 norm squared of A times X divided by Q. And I think this is nice for me, at least, because what we can do is we can say that if we look at A times X and we look at this as a vector, basically a typical coordinate of A times X should be approximately equal to the L2 norm of X. But yeah, this is just a difference in normalization. Cool, and sort of the big question we can ask is how small can Q be, right? The smaller Q be, sort of the smaller the dimensional space, the smaller of a dimension that we can embed these k-sparse vectors to. Cool, and I'll talk a little bit about sparse reconstruction, but I'm going to mostly just focus on this idea of the restricted isometry property. But what Candace and Tao showed was that, if A satisfies the restricted isometry property of order 2k, then given A times X, one can efficiently recover X if X is, say, k-sparse. And as I mentioned, this has lots of applications. So this is something that Jarek told me, and I don't know if, he told me, so I haven't exactly verified it. But one thing he mentioned is that a lot of the math that goes into, say, sparse recovery and what we're talking about today also maybe got used in, say, getting this picture of this black hole that was, I think, a big deal about a year ago. So this is something he told me, so I can't verify it for sure, but these are some of the applications of what we're talking about today. Are there any questions so far? So the first thing I'll talk about is this lower bound due to Garnev and Pliskin. And what they showed was that for any matrix A that satisfies the restricted isometry property, it has to have at least k log n over k rows. Cool. So I'm going to switch to OneNote and talk about this for a little bit. And yeah. And let me know if I need to write bigger or anything. So let me first rewrite the definition of the restricted isometry property. Right, so what we want our vector A, what we want our matrix A to do is when we multiply A times X, and we look at the L2 norm squared, and let's just divide by Q. We want this to be equal to, say, 1 plus or minus epsilon times the L2 norm of X squared.
So very quickly from brief instructions and explanations. Others have made similar points.
Sorry, I couldn't hear you. Sorry?
That seemed incidental. I also couldn't understand it, so I muted them. But
Okay.
yeah, they can try again.
Cool. Yeah, maybe I'll keep going. Right, and X is k-sparse. Right, and the theorem that I just put up on the screen was that Q has to have at least, say, k log n over k rows. Well, and I think, yeah, I forgot to mention this earlier, but for this talk, we're not going to worry too much about the dependence on epsilon. Right, so you could, ask, how does Q depend on epsilon? We're not going to worry about that today, but that is something that maybe people care about. Cool. So one thing we can do just to first, get started in thinking about what's going on is try to see what happens when we consider, say, two specific vectors, let's say x1 and x2. We can let x1 be the vector with first k over 2 coordinates 1 and the rest are 0. And x2 is going to be the vector where the first k over 2 coordinates are 0, Then the next k over 2 coordinates are 1, and the rest are all 0. When we can ask, okay, what happens, right? So these are both k sparse vectors. What happens when we multiply A by these vectors? Right, and we know that when we multiply A by x1, if we look at the L2 norm of that square divided by Q, that should be approximately equal to, say, also the L2 norm squared of 8 times x2 divided by Q, right? So these should both be equal approximately to 1 plus or minus epsilon times k over 2. Right, these vectors have L2 norm k over 2, so when we multiply by A and say normalize by Q, they should also have norms, say approximately k over 2. Well, so what this means is that these vectors, they have to live in a ball of approximately k over 2, right? They can't, right, when we look at A times x1 and A times x2, they can't be too far away from the origin. On the other hand, we can also look at, say, the difference between AX1 and AX2, right? We can look at the distance between these two vectors. Right, this is equal to A times x1 minus x2. x1 minus x2 is also k-sparse, right? So this property of this restricted isometry property still tells us something about, what the L2 norm squared of A times x1 minus x2 is. Right, and in particular, it should be approximately equal to 1 plus or minus epsilon times k. Okay, so in particular, AX1 and A times x2, they should lie in a ball of radius, say approximately square root of k over 2, but they should also be far apart from each other. Right, this restricted isometry property says it's that the distance between A times x1 and A times x2 have to be pretty large. It should be about square root of k. When we can maybe continue this, we can maybe let x of I be equal to the vector where we have a bunch of zeros, then a bunch of ones, and then a bunch of zeros again. And so maybe the first k over 2 times I minus 1 will be zeros. Then we have the next k over 2 coordinates will be 1, and the last coordinates will be 0. Right, and everything we said for x1 and x2 applies for all pairs of xi. Right, all xi, A times xi must be in a ball, the same ball of radius square root of k over 2. But they should also be all simultaneously far apart from each other. Right, the distance between A times xi and A times xj has to be pretty large. It has to be about square root of k. Cool, so we know that there's n over k such xi. And so we can get maybe a lower bound if q equals log of n over k by a volume argument. Right, each of these A times xi's must live in a ball of a big enough radius, and none of the other A times xi's can be in that same ball. Because if they were in that same ball, they would be too close to that the first A times xi. Cool. So this gives us a lower bound of log of n over k. And what I promised you was a lower bound of k times log of n over k. So there's one slight modification we can do. We can maybe allow these A of xi's to be a little bit closer to each other, right? It basically, when we looked at the original A of xi's, they all had to have a distance of, about square root of k from each other. right? And they were basically all non-sparse on different coordinates. Cool, so then maybe if we say allow the distance between x of I and x of j squared to maybe instead of having to be exactly k, we can let it be k over c for some constant k, for some constant c. And this will be for all I and j. Then in this case, we can come up with, say, n over k to the omega of k, such xi. And the same properties still hold, right? These a times xi still have this live in a ball, and the distance between any pair of axi and axj has to be still pretty large. Maybe not square root of k anymore, but now it's going to be about square root of k over c. Cool, and then by the same volume argument, we get this lower bound of k times log of n over k, since we have that many more vectors. Cool, so are there questions about this? Cool, so I'll go back to the slides. Cool, so now we have our lower bound, right? And this lower bound is going to be for any matrix that satisfies the restricted isometry property. Cool, so now we'll start talking about, approaches for an upper bound. What are some actual matrices that might satisfy the restricted isometry property? Cool, and one first step that we can take is, we can maybe let the entries of A be uniform and independently uniform over 1 plus minus 1, and they should obviously also be independent entries. Right, this is maybe kind of a natural idea, and it turns out that this works. And what we can show is that if Q is right, if we have, say, k log n entries, then A actually satisfies the restricted isometry property of order k. Right, so this means that if the entries of A are uniform over plus minus 1, then we can actually get sort of an optimal matrix that satisfies the restricted isometry property. Are we going to get a matrix that satisfies RIP with an optimal number of rows? Cool, so I'll talk about this. And I'll go back to OneNote. So I'll just rewrite the definition of the restricted isometry property. We want the L2 norm squared of A times X to be approximately equal to 1 plus or minus epsilon of the L2 norm of X when X is K sparse. Cool, and now we're going to let A have entries of A are going to be IID over plus minus 1. And what we're going to show is that if we have, say, C times K times log n entries, rows, that's actually enough. So we can take a look at what this matrix looks like, right? It has plus minus ones everywhere. And we can maybe for now just focus on what happens when we multiply it by a single K sparse vector. Well, so for simplicity, we'll let the non-sparse entries or the non-zero entries be the first K, and we'll let the last entries all be 0. Right, and this is going to give us a Q dimensional vector. And let's call these entries A1 all the way up to AQ. we can take a look at, specifically what one of these AIs looks like. Well, so one specific AI is going to look like, plus minus x1, plus minus x2, and so on, all the way up to k, where the plus minus are ID. Right, so this is a random variable that we know pretty well, right? In particular, we know that the A of I are distributed, like a Gaussian, centered at 0 and with standard deviation, x1 squared plus x2 squared. Oh, sorry. All the way up to x k squared. Let me rewrite this. Cool, and sort of the actual value we're looking at is, the value a1 squared plus a2 squared all the way up to aq squared, right? This is going to be equal to a times x, the L2 norm of a times x squared. And we're dividing by q. Cool, and if we sort of do the computations, it turns out that this concentrates around the L2 norm squared of x, right? x1 squared plus x2 squared all the way up to xk squared. Cool. In particular, if we say, look at the probability that, our L2 norm of the resulting vector a times x divided by q is not, good enough to satisfy the restricted isometry property for the specific x, right? So it's not equal to, say, plus minus, 1 plus or minus epsilon times the L2 norm of x where this is bounded above by some exponential times some function of epsilon times q. Cool, so this is an upper bound that we get for some, right, that we fail to satisfy the restricted isometry property for one specific vector x. Cool, and I think one thing just to maybe quickly point out is that, what this is kind of saying is that, we need, say, a constant, if all we care about is just one vector x, we only need, say, a constant number of samples, or A only needs a constant number of rows for us to satisfy the restricted isometry property. Cool, so this will be a sort of a contrast for when we talk about subsampling Hadamard matrices, but yeah. Cool, so this is just for one vector x, and it turns out that it's enough to consider a net of all k-sparse vectors. Right, because if once we have a net of all k-sparse vectors, we can say that for every k-sparse vector, it'll be close to one of these vectors in our net. Right, so as long as we satisfy the restricted isometry property for the vector that it's close to, we'll also satisfy the restricted isometry for this k-sparse vector. And the size of this net is going to be n to the k. This is going to be the number of choices for non-zero entries. times some polynomial and say k times 1 over epsilon. And so we can do a union bound over all the vectors in our net. And that's going to give us a total probability of n to the k. Poly k 1 over epsilon also to the k. So this is the total bound on the failure probability is going to be n to the k times poly of k times 1 over epsilon to the k. Times e to the minus, say, f of epsilon times q. Cool, and this will be small if q is, say, equal to c times k times log of capital N. Cool, and again, I'm ignoring sort of the dependence on epsilon, so there should be some epsilon in this constant, but otherwise it's just going to be k times log. Cool, so are there questions about the upper bound for independent entries? Cool, so let's go back to the slides. Right, so just to recap what we've done, we've shown a lower bound of k log n, and we've shown an upper bound of k log n. Right, so this kind of seems like we're done, right? We've found how to come up with matrices that sort of do as good as you can when we're trying to satisfy the restricted isometry property. But there are a few issues with sort of having our entries be completely random. One is that it requires a lot of randomness, right? We need a different, we need a random bit for every single entry. And also, when we're actually doing the multiplication of a times sort of our k-sparse vector, right? This multiplication will be slow because there's really, we don't have any structure in our matrix A, right? It's completely random. And basically the counterpart is, when we start talking about Hadamard matrices, there's a way to do multiplication where it's much faster, right? And because we are using these for like, taking pictures of black holes or reconstructing pictures of black holes, like we want fast multiplication. Cool, so at this point, I'm going to start talking about Hadamard matrices, which is what the subject of the corresponding paper is about. Cool, so there's a few ways you can define Hadamard matrices. One is this recursive definition where we start with H of 1. It's just going to be the 1-by-1 matrix that's 1. And then we define H of n to be this block matrix where the upper right, upper left, and bottom left blocks are H of n minus 1. And the bottom right block is minus H of n minus 1. When at this point, it will be super useful to index our coordinates by f of 2 to the n rather than capital N. And the reason for this is that, if you look at, say, sorry, there should be H of n, but if we look at, say, H of n, if we look at the I comma jth entry of this matrix, this is going to be equal to minus 1 to the inner product of I and j. Right, so this will be useful when thinking about Hadamard matrices. Hadamard matrices are an isometry, right? When we multiply a Hadamard matrix by itself, it's equal to the identity. And then what this means is that, sampling enough rows of H should work, right? So it's maybe not super clear that, we can get even close to like k log n, but, let's say if we sample enough rows that we sample like each row many different times, that should at least give us a matrix that satisfies the restricted isometry property. It's not going to be a very good one, but it would work. Cool, so just to sort of write down what this matrix A looks like, when we're sampling rows of our Hadamard matrix, we're basically sampling Q vectors, S1 through SQ. They're going to be uniform and independent over F mod 2 to the n. And if we look at, say, the A I comma jth entry, of A, that's going to be equal to -1 to the inner product of S of I and J. Cool, so this is basically what our matrix looks like when we're sampling the rows of our Hadamard matrix. Well, so the rows of A are rows of H of N. And one thing to kind of keep in mind is that the columns of A are very, very dependent. Right? Once we know, say, the column corresponding to the vector 1, 0, and so on, and the column corresponding to the vector 0, 1, 0, and so on, that's going to tell us exactly what the 1, 1, 0 column is. I mean, that's because of the structure of A. Cool. So a lot of the techniques we use when we're analyzing, say, matrices where the entries are completely independent won't work here. But what's kind of nice is that we're still able to get pretty close to this K log n lower bound, right? So what Candace and Tao showed was that we can actually get, this actually gives us a matrix that satisfies the restricted isometry property if we have, if we sample K times log to the 6 of n rows. And then people improved this over a long series of work. Rudelson and Rashinin got an upper bound of K log n log squared K log n. Chirag G. Guruswamy Velinker got an upper bound of K log cubed K log n. Bourgain got an upper bound of K log squared of n, which I think is incomparable to the previous upper bound by Chirag G. Guruswamy Velinker. And then Haviv and Regev got an upper bound of K log squared K log n, which is better than the previous upper bound because K is less than n. Right, so we kept decreasing and decreasing and getting closer and closer to K log n. Right, so, I mean, I think when I saw this, I was like, okay, well, like, K log n seems actually like quite plausible for Hadamard matrices. I don't know if this was me being naive or, I don't necessarily know what people actually taught, but one maybe you can think, basically looking at these series of work is that, eventually we'll get to K log n even for subsampled Hadamard matrices. Cool, and what we showed was that, you actually need K log n samples. Yeah, I think this should be updated, but if K is bigger than, like, say, log to the C of n, or this should really be K times min of n over K. Right, but basically, in for a lot of settings of K, you actually need K log n samples in order to satisfy the restricted isometry property. Cool. So I'll talk a little bit about the ideas and the proof of this. Cool. So let me just actually write the definition of the restricted isometry property again. Right, we want the L2 norm of A times X to be approximately equal to 1 plus or minus epsilon times the L2 norm of X. Right, and in this particular setting, as we have S1, S2, all the way up to SQ, they're uniform and independent over F mod 2 to the n. And in particular, A of I comma j is going to be equal to -1 to the inner product of S of I and j. Right, so in particular, A is going to be a matrix whose rows are indexed by Q, whose columns are indexed by F mod 2 to the n. Cool, so we can try the same approach as before, where maybe we can first focus on a specific k-sparse vector. So let X be our k-sparse vector. And think about what happens when we're multiplying A by X. But as I mentioned before, this time it really, really matters which coordinates are the ones that are non-zero, right? Because this kind of tells us a lot of, right? And just, yeah, it matters more than in the independent case. So as a first step, we can consider the case where the non-zero coordinates are, say, basis vectors, right? So let's say they're E1, E2, all the way up to EK, right? So where E1 is, say, 1, 0, and so on. E2 is going to be, say, 0, 1, 0, and so on. And if we look at what A times X, if we look at the jth coordinate of this, what this is going to look like is -1 to the inner product of Sj, E1 times X1 plus -1 to the inner product of Sj, E2 times X2, and so on and so forth, all the way up to -1 to the inner product of Sj, Ek times Xk. And basically, all of these -1s to the Sj, E1, -1 to the Sj, E2, and so on, these are all going to be randomly plus -1, and they're all going to be independent of each other. Right, we're picking these Sj's uniformly over F2 to the n, right? And basically the inner product of Sj and E1 is going to be the first coordinate of Sj. The inner product of Sj and E2 is going to be the second coordinate of Sj, and so on and so forth. Right, and obviously the first coordinate of Sj has nothing to do with the second coordinate of Sj, and the second coordinate of Sj has nothing to do with the third coordinate of Sj. These are all completely independent. So the analysis here is the same as in the case of IID entries. Cool, and in particular, what this means is that we don't want to focus on these vectors when we're trying to say come up with this better lower bound. So the next maybe set of, the other set of non-zero coordinates we can try are ones that maybe make up a subspace. Right, so maybe we can think of, say, the coordinates corresponding to the 0 vector, E1, E2, all the way up to E of log K. And then say E1 plus E2, E1 plus E3, and so on, all the way up to E1 plus E2 to E of log K. Right, so in particular, this might be this might correspond to a subspace V of dimension log K. Cool, in particular, we can also just let, say, X be a 0, 1 vector. Right, so we'll let X be the vector where it's 1, where it corresponds to an element in the subspace, and 0 otherwise. Right, just to make things a little bit even simpler. Cool, so if we do the computation and look at A times X and look at the jth coordinate, this is just going to be equal to the sum of all vectors V in our vector space of the inner product of -1 to the inner product of S of J, comma, V. Cool. And now we have two cases. If the inner product of S of J, comma, V is equal to 0 for all, if inner product of S of J, comma, E of I is equal to 0 for all I and say 1 through log K, right, then A times X, the jth coordinate, is going to be equal to K exactly, right? Because everything we're adding up here is going to be 1. The other case And otherwise, we know that the inner product of Sj and Ei is equal to 1 for some I. Then basically we know that the inner product of Sj and V is not equal to the inner product of Sj and E of I for all V inner vector space. Right, so this means that when we're adding up, when we're looking at this sum, for every -1, there's also a +1, right? And in this case, A times X, the jth coordinate is going to be equal to 0. Cool, so in general, if we look at say any specific coordinate of A times X, this is going to be equal to K with probability 1 over K. Right, we have that S of J and E of I, the inner product of this is 0 for all I with probability 1 over 2 to the log K or 1 over K. And otherwise it's going to be 0. Well, so what this means is that we're pretty likely to get, when we're looking at the specific vector X and we're looking at A times X, we're very likely to get a lot of zeros. Right, and if we only get zeros, that means that when we're multiplying A times X, we're getting a vector that's 0. This is not anywhere close to the L2 norm squared of X. Right, so this is really bad. We're not going to satisfy the restricted isometry property. If when we multiply by K sparse vector, we're going to get a 0. But the thing is that A times X is going to equal 0 with probability 1 minus 1 over K to the Q, which is approximately equal to E to the minus Q over K. Right, and if A times X is equal to 0, we don't satisfy RIP. Right, we're pretty far from it. Well, so the intuition, I had when I was thinking about this is that, okay, this is the case for one specific subspace of dimension log K. There's something like, say, n to the omega log K subspaces of dimension log K. Right, and let's say we try to do a union bound. This would give us, say, n to the log K times E to the minus Q over K. Right, and this kind of means that Q should be at least K log n log K. Cool, so in particular, for each one of these subspaces, we need, say K samples in order to get something that's even non-zero. Right, and if we kind of try to do a union bound over, say, all n to the log K subspaces of dimension log K, this means that, we kind of need K times log n times log K samples in order to make sure that just none of these vectors are 0 when we multiply them by our potential RIP matrix. Cool. Sorry for scrolling down like this. Well, obviously the issue with this is that the union bound is an upper bound. Right, so this doesn't actually give us anything that we can work with. But instead we can just get around this by using the principle of inclusion-exclusion or the second moment method. Both will end up giving us the right lower bound that we need. Cool, so in particular, the lemma that helps us here is that if we know that, say, the dimension of the intersection of two subspaces is, say, less than or equal to log K over 2, then A times the indicator vector of the first subspace being equal to 0 and A times the indicator vector of the second subspace being equal to 0, they'll be close to being independent. Right? They won't be totally independent, but they'll be close enough because their intersection of the subspaces has small dimension. And this will be enough to give us a lower bound on the probability. A lower bound on the probability that one of these vectors is equal to 0, or one of these A times x's is equal to 0. Right? And if A times x is equal to 0, this is really bad, and we don't satisfy the restricted isometry property. Cool. Are there questions about any of this? Cool, no questions. Let's go back to the slides. Cool, so this is our lower bound. So I'll maybe talk briefly about ideas for future work. One thing to think about is how can we close the gap between upper and lower bound for Hadamard matrices? All right, so even though this upper bound was k log squared k log n, the lower bound we showed was k log n. Right, so it might be nice to have a matching upper and lower bound. Another thing is, can we do bounds for the Fourier transform over Z mod n? Right, so the Hadamard matrix is basically a Fourier transform over f mod 2 to the n. Right, and this lower bound is very specific for Hadamard matrices. Right, if you try to do the same lower bound for the Fourier transform over Z mod n, or if you try the same exact ideas, it won't work. So it might be nice to come up with maybe bounds for Fourier transform over Z mod n. I should mention that all of the upper bounds I mentioned previously do also apply for the Fourier transform over Z mod n. So the upper bounds still apply, the lower bounds don't. But the original k log n still applies. Cool. The last thing that might be nice is maybe more say explicit constructions of matrices that satisfy the restricted isometry property. Right, so the constructions I gave are all randomized, so maybe it's nice to have, say, explicit constructions. Cool, and yeah, that's it.
All right, thanks for the nice talk. We have a few minutes for questions, if anyone has one. So I'll ask actually about your first question there. So you gave a lower bound, right, which is essentially, you present it as a counting argument, but some analytic version of this counting argument. Do you know, at least if I remember correctly from a long time ago, the upper bounds also, you can sort of phrase them as combinatorial arguments, and then you have to do the analytic versions of those things to get upper bounds. Can you state where the gap is between the upper bound, the log k squared, and your lower bound? Sort of which events sort of seem problematic?
Yeah, so I'm trying to remember exactly how, say, the upper bounds go. Right, so all the upper bounds are they're chaining arguments. So somehow they don't really take into account the difference between, say, if the non-zero coordinates are all say independent of each other versus if they're all say come from a subspace. Right, they kind of, I'm trying to remember exactly. Yeah, I think essentially they kind of treat all k-sparse vectors the same, and they do some sort of chaining argument that I think maybe implicitly kind of deals with this a little bit, but not exactly. And I think one thing that might be kind of nice is if we can say you can sort of deal with, say, every set of, say, possible non-zero coordinates differently, right? So on one hand, for the like if they're all independent, like we don't have any work there. On the other hand, for the case where they all come from a subspace, there's there are like n to the log k, but there's not more. Maybe there's a way to say interpolate between these two. But I think from what I remember for the upper bounds, they don't really differentiate between these two cases beyond, say, maybe like anything that's implicit from the chaining arguments.
Okay. If we don't have any more questions, then we have 3 minutes until, wait, we have more time than that. We have 8 minutes until Sam's talk. So feel free to chat until then.